Hello, my friends. I'm extremely happy to welcome you all from Israel. My name is Oleg Butkovsky, and I'm a researcher at the Weierstrass Institute of Berlin. But right now, I'm trying to hide from the coronavirus here in Israel. Let me start my talk by sharing the slides of my presentation. I hope you can all see them now. So what I wanted to discuss with you today is our very recent progress on ergodicity for order-preserving stochastic partial differential equations in the hyperelliptic setting. And this is a joint work with Michael Shoitzer, who is a professor at Technical University Berlin. So what is this all about? So now in the mathematical physics literature, there is a growing interest towards the stochastic systems where noise enters only in a finite Fourier mode, in finite and many Fourier modes. We can immediately start by considering the following example of stochastic reaction-diffusion equation. So here we have the usual stochastic reaction-diffusion equation with some cubic nonlinearities in the drift. The specific form of the drift will not be important for us at all. But what we see here, what is interesting for us and what will be crucial, that the noise is not space-time white noise, which acts like uniformly in space. Instead of it, we see that the noise acts only on the first n Fourier components, and then in the remaining components and the remaining infinite many components, there is no noise. So the system behaves in a deterministic way somehow. Or we can say that the noise gets to the component starting from n+1 because of the noise that we entered in the first n component. And there is now a really big interest to such systems. And of course, people study not only stochastic reaction diffusion equation, there are many famous works by Martin Heyer and Jonathan Mattingly about Navier-Stokes equations. People study some hydrodynamic equations, some Boussinesq equations, many other equations. The common subject is that the noise is not space-time, is not white in space. It doesn't act on all components. Rather, it enters only the first finite and many components. Now, what is special here? On the one hand, so here we assume that these sigmas are some very nice smooth functions. And it is indeed relatively easy to show that this system is well posed, that it has a unique strong solution, and it's a Markov process. But what is going on also, that because the system does not get enough noise, it is not strong failure. It is only failure, but not strong failure. And this makes analyzing their ergodic behavior, establishing whether there exists a unique invariant measure, much more complicated than if it would have been strong failure. So let me maybe take one step back and explain you what is in general known for this kind of process, which are failure but not strong failure. And one can think about his or her favorite stochastic partial differential equations or stochastic delay equation. They all share these issues. So up until the early 2000s, there was really no theory for proving it. There was a seminal book of Main and Tweedy, but these books deals only with strong failure processes. And the breakthrough was achieved in a series of papers of Heyer and Mattingly, and then Heyer, Mattingly, and Shoitzer, who suggested so-called asymptotic or generalized coupling approach. So if you have a strong failure process, you can do your coupling. And here, for some reasons, unfortunately, I don't have so much time, but I would be very happy to go into details during our discussion sessions. Building an exact coupling is complicated, but one can construct something what is called asymptotic coupling. And indeed, using these asymptotic couplings, Heyer, for example, showed that this equation that I wrote, if n is large enough, then this equation has a unique invariant measure. Another approach based on the notion of the so-called D small set was developed by Heyer, Mattingly, and Shoitzer, and late in my work. And again, it's some very general approach that provides some sufficient conditions for unique ergodicity and exponential convergence or sub-exponential convergence to the invariant measure for such processes. And then there is also a very famous approach based on the notion of asymptotic strong failure property developed in this Annals of Mathematics paper of Heyer and Mattingly. And what do we have here? So the conditions of the D small set approach are they're really general, but they're very hard to check. On the other hand, the conditions here If we talk about, for example, asymptotic coupling approach, they are easier to check, but they might be not so accurate. And so what we suggest here, we suggest a completely new approach, which is orthogonal to all the approaches before, because we assume additionally that the Markov process is order preserving, and we want to gain from this. So all these approach, of course, they don't care about order preservation, and then they provide some general results. And our observation with Mikhail Shoitzer was that if your specific process is order preserving, like, for example, stochastic reaction-diffusion equation, then you can do different things and obtain better results that you can get with all the above techniques. Let me now show you exactly what we have achieved. So again, so this is all called stabilization by noise. So let's say we have this stochastic reaction-diffusion equation, and we want to ask a very simple question. What is the smallest number of n? So what is the smallest number of Fourier modes I need to activate so that this guy has a unique invariant measure? On the one hand, if you don't activate any Fourier modes, if you just consider this deterministic equation, then it is relatively clear that this deterministic guy has three invariant measures, right? So your process can be identically 0, identically 1, identically minus 2. This is clear. If n is infinity, if you have here space-time white noise, which acts on all modes or something similar to it, then under certain conditions of sigma, your process will be strong-Feller, you have exponential convergence and collaboration, everything is classical, and this is due to the Pratt transaction. If n is large, then the uniqueness of invariant measure and exponential convergence was due to Feirer, who used a asymptotic coupling approach, as I mentioned before in my previous slide. Later, in 2011, Feirer and Mattingly used techniques based on asymptotic strong-Feller property and Malevin calculus to show that if you excite only 3 modes, then this is already enough for unique ergodicity. And our result with Michael Shoitzer is somehow not improvable, because we showed that already if you excite only 1 mode, so if n is 1 and your sigma satisfies some natural condition, let's say it's always bigger than some epsilon, right? So it's non-degenerate. Then already this is enough for exponential convergence and uniqueness of invariant measure. And this happens because this process is order preserving, which of course was not taken into account into all the previous results. Okay, so now let me maybe very quickly say what is it about, what is order preservation, and maybe I will explain how we can gain from this. And then we will leave a more detailed discussions to your questions and live sessions. So let us say we have a Markov semigroup over some space E with partial order. The semigroup is called order preserving if for any bounded increasing function f, the function PTF is increasing. So let me recall that Feller processes, they maps continuous to continuous, and this is what people study. Strong Feller, they maps bounded to continuous. And what we study, what we suggest that is should study, we want to study semigroups which maps increasing to increasing. And so you see why our approach is somehow orthogonal and different from the approaches that people took before. There is also a coupling definition. So right. So if you start your Markov processes with 2 points, one below another, then at any time, let's say at time 1, we can construct a coupling such that this process at time 1 will still be above this process at time 1. Okay, so you start two Markov processes, one above another at time 0, and then this can be conserved, this relation, also at time 1. So at time 1, their trajectories will also be in the same order. And examples of such semigroups include one-dimensional stochastic differential equations, stochastic reaction-diffusion equation that I mentioned, porous medium, and some other examples. And let me now present our main results. So now somehow I claim now that if if your system is order preserved, then you need only very mild conditions, very weak conditions, and very weak additional and natural conditions for unique ergodicity and exponential convergence. Namely, if the semigroup is order preserving, and assume also that there is recurrence condition, right? So So it's not like Brownian motion, which will just never, so it's like leave zero and we never see it again. So some existence of Lyapunov functions. And also what is important for me is what we call the large drop condition. It means that if I'm in a ball, like in a certain ball of radius m, that I can drop, let's say, with very small probability, but at least with positive, that I can drop below some element, or I can drop above element, right? So I start in a ball, and then there is like a fixed, I can divide my space into two parts, such that with small probability, I will be in one part of this space, and with maybe also small probability in another part of the space. And then it turned out that that's it. That once we have these conditions, then the semigroup has a unique invariant measure and exponential convergence. Okay, and these large drop conditions, so if you don't have it, it's relatively easy to see that nothing can happen. Maybe just the system will stay at its place and still be perfectly order preserving. And in many cases, checking that this condition is satisfied is not so difficult. And so now it's indeed possible to check that this holds for reaction diffusion equations. And so as I mentioned before, so there is a paper of Hieromartin showing exponential ergodicity when the noise acts on three modes, one cosinus and sinus. And our results show that already if node acts only on one mode, so n is 1, and this function sigma is everywhere positive, this is enough for unique ergodicity. And let me maybe conclude by providing you some reference and also mention a very interesting paper by Ben Guess and Pablo Sassoulis, who used these ideas and developed them to show synchronization by noise for 542 and 543 models. Because indeed it turned out, so this 542 and 543 system are of course also order preserving. And then it turned out that similar ideas can allow you to establish for these singular PDs also synchronization by noise. So I hope you enjoyed my talk, and I hope to see you all during our live discussion session. Thank you very much.